Today we are going to explore a paper entitled VCTD Terraform C Data Analytics in the Cloud using SGX. And this paper has been published in 36 IEEE Symposium on Security and Privacy in May 2015. Auckland, the venue, is considered as one of the best venue in this security and privacy research track, and this paper belongs to Microsoft Research and is considered as one of the best security and privacy research work which targets IntelSGX and big data analytics. I am Said Mofrad, the presenter. This paper introduces VC3, which is the first system that allows users to run distributed MapReduce computation in the cloud environment, while it keeps the code and data secret. Also, VC3 ensures the correctness and completeness of the results. That means VC3 provides the job execution integrity protocol. Also, VC3 runs on unmodified Hadoop, and it is fully compatible with the current implementation of Hadoop. And as an option, VC3 enforces region self-integrity invariants for all MapReduce code running within isolated regions or the enclave to prevent attacks due to unsafe memory access, such as reading and writing. VC3 secures the MapReduce framework. Basically, MapReduce is a popular programming model for processing big data workloads. In the MapReduce, users write the map and reduce functions, and the execution of both functions is automatically parallelized and distributed in the cloud environment. So as you can see in the picture, in MapReduce job, in the first step, in the splitting step, the framework breaks raw input data into input splits. In the next step, input splits are distributed between mappers node, and after that, each mapper node parses its splits into input key value pairs, and then calls the map function on each of them to produce the intermediate key value pairs. In the next step, the framework groups these pairs by key and distributes them between reducers, which means the framework is doing the partitioning and shuffling process. And finally, in the last step, each reducer node calls the reduce function on set of all the values with the same key to produce the output key value pairs and returns the result to the user. VC3 is using Intel Software Guard extension as its trusted execution environment to secure the MapReduce job workflow. In a nutshell, Intel Software Guard extension provides the capacity that a user application software can create an isolated area, which is called the enclave. The hardware protects the confidentiality and integrity of the enclave, which is the isolated area. As we can see in this execution flow, so every SGX application is created with two different parts, trusted and untrusted parts. The untrusted parts creates the enclave, which is placed in the trusted memory in the platform, and after that, a function inside the untrusted part calls another function which is located inside the enclave and the trusted part, and at this moment the execution flow is transferred to the enclave safely. When the execution reaches to the enclave, the intended task and function is executed inside the enclave, where all data will appear in clear text, and after that the results will return to the caller function inside the untrusted part. And after that, the normal execution of the application will continue. The important point in SGX platform is that the privileged system code, OS, and virtual machine monitor or BIOS or system management mode, which all of them have the higher privilege access to the system. They cannot see the enclave data in clear text. And what they can see is just the encrypted data. So the integrity of the data and the confidentiality of the data inside enclave will preserve. In the Intel SGX, the security perimeter is the CPU package boundary, which means data and code, all of them are unencrypted inside the CPU package. And everything outside of the CPU package is encrypted and their integrity will be checked. So when we have this protection, external memory reads and bus snoops, which are considered the kind of system level attack, they can only see the encrypted data. As we can see in this image, so the information in the system memory is some encrypted value, but when that encrypted value reaches to the CPU cache line, that belongs to the social security number of a person. Here we explain the VCTD adversary model assumptions. VCTD assumes a powerful adversary who may control the entire software stack in a cloud infrastructure, such as hypervisor and the OS. Also, VCTD assumes the adversary may also record, replay, and modify or drop the network packets. In addition, VCTD assumes the adversary may read or modify data after it left the processor using I/O probing, DMA, or similar attack techniques. Furthermore, the VCTD assumes the adversary may access any number of other jobs running on the cloud, and also the user map and reduce functions. VCT assumes they are benign, but they may have some low-level defect in the code, in the user code development, which leaks the information. In addition, adversary cannot physically open a Intel SGX processor package. VCT assumes the Intel cannot be breached, the Intel security, the CPU package security cannot be breached. And also VCT does not consider the denial of service attack, network traffic analysis attack, and some side channel exploits and fault injection kind of attack. VCT does not consider those in this protection model. Here we have the VCTD design overview. In the VCTD, a user implements MapReduce jobs in the usual way. The user writes, tests, and debug map and reduce functions by using the C++ development tools. When the map and reduce functions are ready, the user compiles and encrypts them, which obtaining the private enclave code referred to as E-. So the user binds the encrypted code, E- encrypted code, together with a small amount of generic public code referred to as E+. E+ implements the key exchange and job execution protocol in the VCTD. After that, the user should upload a binary containing the enclave code to the cloud along with the encrypted input data to the remote cloud. At that moment, enclaves containing E- and E+ are initialized and launched by the public and untrusted framework. Here is referred to as framework F. on every worker nodes. So in the VC3, the intention is to decrease the amount of TCP. So the interface between the trusted and untrusted app is very narrow. Basically, we have two function calls, read key value and write key value. Uh, so other than relying on that narrow interface, the code in the enclave is self-sufficient, which means there is no outside dependency. And it makes sure that the TCP or trusted computing base inside the enclave is kept small. This slide visualizes the VCTD high-level concept of enhanced MapReduce job. So as we can see in this slide, code and data are always, they are appear encrypted when they are in the untrusted part of the platform, and they are out of the processor. And they are only appear in clear text when they are inside the processor. Both code and MapReduce related data, as you can see in this figure. So at the same time, the single execution thread is allowed inside the VCTD enclave execution runtime. So in order to have the parallelism, the solution is to running the many instances of the map and reduce functions in the cloud. So VCTD mainly does this to protect the enclave execution from well-known synchronization attacks which can be applied on the multi-threading applications. So as we can see, only inside the processor chip, the user map and reduce function run on plain text. Here we summarizes the VCTD job deployment and execution flow. So in first step, user prepares and compiles the enclave code to deploy the enclave code and the MapReduce encrypted input data in the remote untrusted cloud. So as soon as the code is arrived, it is loaded into enclaves in worker nodes in the cloud, and then it executes the key exchange protocol, which comes with the E plus code or generic code inside the enclave to get the cryptographic keys to decrypt the user private code, which implements the MapReduce functions. As soon as the user MapReduce functions get decrypted, in third step, the worker nodes executes the job and the verification protocol. So in VCTD, we have a Glue code. The framework code F actually implements the Hadoop streaming interface that binds the unmodified Hadoop deployment. So when we have this framework code F, the VCTD's map and reduce nodes looks like the regular worker nodes to the Hadoop. So the VCTD SGX applications is transparent to the original unmodified Hadoop. VCTD to make a trust between its framework and the enclave which is executed in the remote cloud needs the cloud quoting enclave. Basically, VCTD defines it as a complement quotes by the SGX quoting enclave, which is usually used to measure the enclave signature and make a trust in the SGX applications. So basically, the cloud quoting enclave intention is to stating that the enclave runs on hardware which is owned and certified by the cloud provider in the certain data center. So VC3 needs this because there could be one adversary that has the genuine Intel SGX, but actually that Intel SGX doesn't belong to the certain data center. So we need that cloud coating enclave to take care of and address that kind of adversary attacks. So in order to create the cloud coating enclave, the cloud provider itself creates that cloud coating enclave when the cloud includes a new SGX enabled system. So then this cloud coating enclave generates the pair of keys, public and private key, and it outputs and shares the public key and seals the private key, which never leaves the cloud coating enclave. And as we can see in the signature model, in the following, VC3 relies on two fixed signing identities. One of them belongs for the original Intel SGX, and the second one belongs to the cloud. So as you can see, they have the model to sign the enclave measurement by the SGX coating enclave and also cloud coating enclave to make a trust in the public cloud environment. Before starting the actual job, VCTV needs to run the key exchange protocol to distribute the encryption key of the private enclave and also the encryption key for the actual MapReduce job encrypted input files. So in order to complete this exchange protocol, we need three different messages. In the first message, the user chooses a fresh job identifier, so-called J, and generates a fresh symmetric key, referred to as key code, to encrypt the private enclave code, then sends to any node involved the code for its job enclave, referred to as CJU. As we can see here, CJU is equal to the public enclave code concatenate with encrypted value of the private enclave code concatenate with job identifier and the public key of the user that this job belongs to. In the second message, every node omega gets this message from the user, and by using that CJU, they initialize the enclave, and the E plus pulse of that enclave derives a symmetric key belongs to this node, referred to as key omega, and the E plus encrypts this key omega with the user's public key. So at this step we have M omega, which is the public key encryption of the key omega, which belongs to the specific node. Also, after this creating this message, so the E plus requests the codes from the SGX platform and also the cloud platform, quoting enclaves, and sends that message in omega to sign the enclave measurement for that. So because every encryption here uses the authenticated encryption, the CJU is also included with the encryption phase. So as we can see here, the encrypted message PW has the plain text value of the MW. Actually, MW is also the encrypted value concatenated with the signature of the MW, um, um, which is authenticated by the job information which has been arrived. So basically, the MW is the message, and that right side the encrypted value is the authenticated information. So now we go to the message tree. In message tree, the user processes a message PW which receives from the every node omega. And in the process, the user verifies that both quoting enclave, the cloud quoting enclave, that S6 platform quoting enclave, have signs the message omega under the identity CJU, which has been sent initially in the first message. And then after that, the user decrypts the omega with its private key and responds a job credential, um, which is encrypted under the resulting node uh, key W, which belongs to the particular enclave. So job credential omega, which belongs to a specific node, is equal to the encrypted value of the key code concatenated with K, where key code is the key that protects the code E minus and K is list of key. So basically, K is a set of authenticated encryption keys which is used in the actual job execution. So particularly, uh, K job is used for protecting the verification messages, while the K in, K inter, and K out are used to protect the input splits and intermediate key value pairs and output key value pairs respectively. So finally, key pseudo-random function of key_prf is used for keying the pseudo-random function prf, which actually is part of the mapper codes to implement the shuffling process and to finding the proper reducer identity in the actual Java execution. After that, every node in the cloud continues the E plus code with the job enclave, and then now they have the key, the credentials, they decrypt the job credentials with their own key, and after that now they can decrypt the private code segment E minus by that key code, and then they can have access to the map and reduce code which is inside the E minus, and then they can execute the job. VCTD uses the job verification protocol to check the job integrity, execution integrity. So as we can see in this diagram, so in the we have different steps: setup, execution, and verification. In the setup step, the user decides on a subset of all available input splits as input for the job, and then decides a number of logical reducers for the job referred to as capital R. After that decision making, it sends the job specification securely to its verifier. And the user does not decide about the mapper, because usually Hadoop framework decides about the number of mappers. So then in the execution part, at the mapping part, Hadoop distributes input splits to running mapper instances. The mapper wrap the plain text intermediate key value pairs in encrypted intermediate key value pairs referred to as KV inter. Also, for verification purposes, After mapper processed all the inputs split, the mapper will produce a special closing intermediate key value pair to be sent for the reducer. So that closing intermediate key value pair is an authenticated message which ensures that every reducer knows about the total number of intermediate key value pair it should be expected to receive from the mapper. So in case a reducer does not receive exactly this number of key value pair or receives the duplicated key value pairs, it terminates itself without outputting its final verification message. Furthermore, each mapper sends the final verification message to the verifier referred to as capital FM. Now, assuming that the Hadoop correctly distributed all intermediate key value pairs referred to as KV inter and also the KV close, the closing messages, the reducers produce and encrypt the final output key value pairs for the job. Also, for the verification purpose, reducers, after getting the job done, by verifying all key value pairs KVA inter and KVA close which has been received from the mapper, they will send a final verification message to the verifier. So as we can see, we have one layer of integrity protection which happens by the by the reducers and one which happens by the verification module. So in step 4, the verifier receives a set of FM and from mappers and a set of FR, which is the closing intermediate job message for reducers, and then it starts the verification. To verify the global integrity of the job, the verifier first checks that if received exactly one FR from every reducer. So if you remember, reducer will terminate itself. So the verifier has a number of total reducers. So if it sees the number of received reducer messages, they are less than that expected value, it knows the integrity of job has been compromised. This slide visualizes the job execution protocol. So as we can see, verifier module needs to answer these 3 questions. Did mapper process all input data? Do the reducer agree on the set of mappers? Did reducers process all intermediate data? So, and basically by using that FR and FM, and the job specification that register receives from the user, it can verify the execution integrity of the job. So also as we can see in this image, so the intermediate key value pairs packages the plain key value pairs p-value pairs and the job ID and the mapper ID and the sequence number and encrypts them with the AES GSM to be sent by the reducer. And for the shuffling purpose, if you remember, we had the pseudorandom function, which the pseudorandom function uses the uh, key value and after that the modular results of the number of total reducer will define the reducer identity which the mapper should send the value to it. So basically that scheme defines the shuffling step in the VC3 framework. For having the more security, VCT supports the optional enforcing a region right integrity check, which it happens by the UCTD compiler. So the region right integrity tries to guarantee every write by using the pointer will write only to the address taken variable in the enclave or to location which belongs to the enclave heap. So basically, the address taken variable is a variable whose address is taken in the code. For example, the address of operator and for example the array variable, they are considered the address taken variables. In addition, the regional right integrity guarantees that the indirect call instructions in the code can only target the start of the address taken function in the enclave, and they cannot leak the information outside of the enclave. So basically to implement this, VCTD creates a bitmap to record which memory area inside the enclave are writable, and that bitmap maps every 8 bytes slot of enclave memory to 1 bit, and the integrity invariants are enforced with the dynamic checks on enclave read, write, and control flow transitions. So basically, the compiler inserts dynamic checks when it cannot verify the safety of memory operation or control flow transaction at compile time. So that feature should be enabled by the compiler when the user creates the enclave code, actually when it binds the E- and E plus code, so to add this protection layer. Enforcing region read-write integrity furthers the integrity enclave integrity check protection. Basically, it includes the region write integrity guarantee and adds the guarantee that reads through the pointer will read only from address inside the enclave. So the last one just monitored the writing through the pointers, and now this integrity adds more protection and also takes it addresses the reading through the pointer. So basically, as we can see, the compiler will add these assembly codes to check the memory that is read. It is inside the enclave region, and basically it will stop the execution if that memory tries to access another memory address which is not belong to the enclave trusted code. For the implementation, VCTD uses the Microsoft the version of SGX emulator. They do not use the Intel SGX SDK because they say SGX is not accurate enough to for their test results. So basically, they create their own SGX SDK, and in order to implement the emulator, they changed the Windows kernel to implement the SGX emulator. They did this because at that time they didn't have access to the real Intel SGX processor, but they had the blueprint of the Intel SGX from Intel. So the VC3 actually implements the compiler that supports the enclave self-integrity invariants and a modification to be a modification to the Microsoft C++ compiler version 18. So basically, that integrity invariant checks is included inside the Microsoft C++ compiler, which can be enabled and disabled. And for the enclave size, their emulator uses 512 megabyte enclave, and they don't implement the memory swapping APIs because usually SGX is bounded to 128 megabytes of memory, and every memory larger of that memory, specifically in the Windows environment is not supported. So they also implemented some tools, for example, the Packer to pack the E- and the E plus enclave code together. And for the testbed, they use the Microsoft Windows Server 2012 release 2 64-bit on workstation with 2.9 gigabytes Intel Core i5 4570 Haswell processor family with the 8 gigabyte of RAM and 250 gigabyte Samsung 840 ever SSD. This table shows the test cases that VCTD used for the evaluation. So basically we have the list of applications and as we can see the key search options and pi are compute intensive jobs and the I/O volume, user usage, and word count are considered I/O intensive test cases. So and also we have the input size and the size of E minus and the number of map tasks that they needed to uh, implement that MapReduce job is available in this slide. This slide describes the performance overhead of VCTD through the baseline, which is the unencrypted and without the protection MapReduce job. And also we have the VCTD-W, which is a write integrity, and VCTD-WR, which is a write read integrity invariant check. So uh, um, as they reported, when the MapReduce is protected by the VCTD, the average performance overhead of the old job is negligible. But when they enable the VCTD write integrity, the performance overhead is resulted 4.5%, and when they enable the VCTD write read integrity invariant check, the performance overhead increased to the 8%. Also, they redo the test in the isolated machine because they claim that the Hadoop and cloud environment has its own performance overhead, and they needed to know what exactly is the performance overhead of the VCTD. So they redo the test in a single machine without the Hadoop. So and we can see, as we can see the result, the I/O volume and user usage, which were the I/O intensive, they had the most um, performance overhead, about uh, more than 1.50 times than the baseline. And as we can see in the graph, for example, the revenue had 1.25 for the uh, VCTD with the write and read integrity check. So basically that graph visualizes the performance overhead, and performance overhead is negligible when the job is um, computation intensive, but the performance overhead is much larger when the job is IO intensive job. In conclusion, VCTD is a novel approach for the verifiable and confidential execution of MapReduce job in untrusted cloud environments. And also, we've seen that VCTD approach provides a strong security guarantee while relying on the small TCP which is rooted in the SGX hardware. And as we can see in the result, VCTD had a good performance, and the VCTD was transparent to the original Hadoop.